Well, good morning. This is 11:04 on Thursday, the 28th of September, 2017. It's supposed to be linear algebra class. However, I'm the only one in the room, so I hope some other students will be coming in soon rather than later, but I have to have you any time. I did want to make a couple of announcements first. If you were looking for me tomorrow, okay, I had one student in the last class who asked when my office hours were tomorrow. Well, I made this announcement at the beginning, but she wasn't here at the time. So let me make it for you now so you'll know this. Normally on Fridays, I'm on the Birmingham campus, 7:45 to 11:45, though most days I'm there much later than 11:45, like last week, way into the afternoon, because we had a meeting that went way too long. And then afterwards still had some discussion, so not too long. However, tomorrow, sorry, my throat's clogged up. We haven't even started class and it's already clogging up. Tomorrow I've got an infusion scheduled for 8 o'clock. That means I have to be at Kirkland Clinic around 7-ish or so. And then the infusion usually takes awfully close to 8 hours. I mean, it doesn't take that long itself, but by the time they get me in, and it'll be this, that, and the other thing, and 30 minutes after the medication before they can start, all that kind of stuff, those protocols, it winds up being almost an all-day affair. I've gotten out a few days before 4, right after 4. Other days it's been awfully close to 4:30, so... Anyway, I will not be on either campus tomorrow because of my infusion. Okay, next week, Mondays are fairly close to normal as office hours. Mondays and Wednesdays right now, I'm meeting with the math team if they're available to meet. That's 3:15 until 4:45. However, we've not met more days than we've met, so sometimes I'm available then for office hours, sometimes not. But all the time between 3:45 and 5:15, and most Mondays and Wednesdays I can stay later if you need to see me then too. However, this coming Monday, we may meet with math team, if so there, but I think I'm going to need to leave right after 5:15 because I've got another meeting off campus that I need to get to as soon as I can. So that's coming up Monday. Normal office hours except for the math team. If it meets, it won't be as long. Tuesday, normally my only office hours then are 12:15, right when this class gets out, until 1:15 when my next class starts. Well, Tuesday we're going on a field trip in my third class, the afternoon class, and I've got to, as soon as we get out of this class, I have to book it to the Birmingham campus and pick up the van for me to take the students to the field trip. So I will leave just as soon as this class is over with and not get back probably until awfully close to 1:15, if not maybe a little later. It just depends on how long it takes to get the paperwork done for the van. Usually they have it ready for me and it's not too long. So Tuesday my office hours are shot too, and then we'll be at Sanford Planetarium the early part of the afternoon. Then we'll be back and finish up class here. I'll be available then after 5:45 again. And then the rest of it is going to be back to normal, whatever normal is. Once second mini-term starts, however, then my office hours change on Tuesday and Thursday. I'll actually have more office hours then because my class won't be starting until 3:15, whereas this one starts at 1:15. So that's coming up. All right. Now, where we left off last time in linear algebra was on page 57. It's Chapter 2, Matrices, 2.2, Properties of Matrix Operations, and the latest operation we did was the transpose of a matrix, which is interchanging rows and columns. Now, here are some properties that you have, and actually we've already sort of hinted at some of these in the discovery block we did last time. But here are these properties of transposes. So here we have that, let me get my pen activated to black. Here we have two matrices, A and B, both matrices, okay? And the sizes are such that the given operations are defined, okay? And C is a scalar. That's all you need to know, just any real number, scalar, okay? Then these following properties are true, okay? One, if you take A, transpose that, and then transpose it again, you've exchanged rows and columns, exchanged them again, you're right back where you started with an A, okay? No matter what size A is, okay? So that's the first one. The second one, if you have the sum of two matrices, A plus B, and do the transpose of the sum. Now, remember it says A and B have to be whatever sizes are required. Whatever size A is, if you're adding it to B, they have to be identically the same size. If A is M by N, B has to be M by N. No question about it. If they're not same size, you can't add them. So if you can't add them, you don't even worry about the transpose. But if you can add them, if they are same size, and then you transpose the sum, then this happens to be the A transpose plus B transpose, okay? And if you think about that, you go term by term when you add, and you're exchanging term by term. So Jasmine's here, and so far Kimmel is not, okay? Get it set up. Since you are coming in now, you may not go back and listen to the first part of the YouTube. So since you might not, let me say what I said then now. If you might have been looking for me, office hours tomorrow, don't bother. Okay, I've got an infusion tomorrow, and I'll be at Kirkland Clinic from around 7-ish in the morning till probably 4 or 4:30 in the afternoon. So I will not be on either campus tomorrow, okay, at all. Okay, Monday will be more normal. You know if we'll be doing math team on Monday or not?
Monday, I think she said we were trying to meet with everybody.
On the Birmingham campus? Okay. All right, well then, we won't be meeting here then. It's all right, okay. All right, well then, that will take care of that. Tuesday, you know, normally on Tuesday and Thursday, I have, the only office hours I have are right after this class during my lunch hour, 12:15 to 1:15. Well, I'm taking my afternoon class Tuesday to Sanford Planetarium for a field trip. So I've got to, as soon as this class gets over with on Tuesday, I've got to book it to the Birmingham campus, pick up the van, bring it back here. We'll go on the field trip, come back, and then in the evening, I take it back to Birmingham and go home from there. So I won't be on campus any time that I'm not in class, basically on Tuesday. I'll be on the road or something on Tuesday. Okay? Then after that, we're back to sort of normal, I guess. Wednesday, or you know if we'll be practicing or not, or is she going to want to meet together? Yeah, we'll find out next week. See. What's that?
I think next Saturday is the tournament.
Yeah, it's a tournament. So that's why I wondered if you wanted.
I don't know.
We'll find out Monday. Yeah. Okay. Let me know Monday or Tuesday then. Yeah. All right. All right. Okay. Or even Wednesday's fine too. I'll see you Wednesday too. Okay. Those are the only announcements I can remember. Okay, we were talking about transpose. You weren't here last time. Do you know what the transpose of a function is, of a matrix is? You interchange columns and rows. Like if you have 1, 3, 5, 2, 4, 6, then the transpose of that would be 1, 2, 3, 5, whatever I said to the other was, yeah, 5, 6. You just interchange columns and rows. If it was a 2 by 3, it becomes a 3 by 2. That's what a transpose is. And these, we're looking at the properties of the transpose. Well, if you interchange rows and columns of one matrix, and then change them again, you're back to the original matrix, right? Okay? If you have the sum of two matrices, now in this case, A and B have to be identically the same size, otherwise you can't add them. But if you add them and then take a transpose, that's the same as taking the transpose of the first plus the transpose of the second. And if you think about it, you're adding term by term anyway, right? And if you transpose one and transpose the other and add them, that's the same as adding them and then transposing them. So that's the same. Okay? The third is if you're transposing a scalar product times a matrix, okay, transposing that, then that's the same as pulling out the scalar product, the scalar, and multiplying by A transpose. Okay? Well, it really doesn't matter if you put the parentheses or not, or where you put them or not, but they put them like that. You really don't need them except to indicate you're transposing first and then multiplying by the scalar. But again, remember, if you're starting with some matrix A, okay, and you multiply it by C, you're multiplying every element in A by that number C, right? Every element by that C. So, guess what? And then you take the transpose of that. That's what the left-hand side does. Well, what the right-hand side does is transpose A first, and then multiply everything. If you're multiplying every element, it doesn't matter whether you do it before you transpose or after you transpose. That's the same. But this one is the strange one. And this one we did in the discovery, and we did it in class, so you can go back and see it. If you have the product of two matrices, A, B, okay, and ultimately we're going to transpose that, but let's pause before we go there. Remember, if you had been here, I said A and B, and the book says it, are of the sizes that make the operations doable, okay? So in this one, A and B had to be the same size, identically the same size before you can add, right? Well, here when you're multiplying matrices, remember they have to be the same size so you can multiply. If A is M by N, then B has to be N by P. The two inner ones have to be the same or else you can't multiply, okay? So, if you multiply two matrices and then transpose that result, this is the one that's a little bizarre, okay? Because that's equal to B transpose times A transpose. Whoa, okay? There are some other things you have to... No, okay, it's fine. Remember, the sizes have to be that the number of columns of A has an equal number of rows of B, right? But then when you, so if this is M by N multiplied by N by P, so let's sort of write it down there, M by N, then B has to be N by something, let's just call it P, whatever that is. So this product has an M by P, because these go out, right? But then when you transpose, it becomes a P by M. Okay? Now, on the other hand, B was an N by P, but when you transpose it, it becomes a P by N, right? A was an M by N. When you transpose it, it becomes an N by M, right? Now that makes it legal to multiply, and when you multiply, you wind up with P by M. Now all this shows is that the dimensions are correct, but in reality, the numbers are correct too. Whatever the values are there, that will work. Okay? So the transpose of a product is the reversed product of the transposes. You have to change the order too. And the reason is because of the size issue. Okay. All right. They do a little proof on some of those. I'll let you take a look at it. And property 2 and 4, they say, can be extended to other things. And let's show you what that extension is. Okay. What if you had A plus B plus C? Now, C is properly sized matrix. In other words, exactly the same size as A and B. If you're going to transpose that, that's going to be A transpose plus B transpose plus C transpose. Okay, so that's just like you would expect. Now this one, if you had a product of multiple matrices, A, B, C, and you're going to transpose that product, what would you guess? C transpose B transpose A transpose. You're absolutely right. Okay. So, however many products you have. Now, of course, in this case, A, B, and C have to be the sizes that you can multiply. So if this is a L by N, B has to be an N by P, and C has to be a P by Q. You know, and then when you transpose, the product is going to wind up being an A by Q. When you transpose that, it becomes out Q by A. And sure enough, if this was a P by Q, this becomes Q by P when you transpose it. That was an M by P, it becomes a P by N. And this was an M by N, it becomes a, yeah, it all works. Okay. So let's do some examples with those properties. Any questions before I go? Okay. Let's show that AB transpose is B transpose A transpose. Okay. Here's A. 2, 1, negative 2. Negative 1, 0, 3. 0, negative 2, 1. Here's B. 3, 1. 2, negative 1. 3, 0. Okay. What we're I don't know if you've noticed, I tend to clog up in this room. Here's now my current thinking of what's happening. Usually they don't turn on the ventilation system until right before 8 o'clock, sometimes right at 8 o'clock. So the room has gotten, there's no air conditioning then. My 8 o'clock class on Tuesday, Thursday is almost a full room. It's got 30 plus students enrolled in it, and just about always the vast majority are here. So somewhere in the neighborhood of 25, 30 people in the room. So they just turn on the AC system, but it doesn't get very chilly because we got all the people in here. My second class then is 17 students, so you don't lose a lot then either. Today, we started with fewer than that, but they build up. I think all but 2 showed up. So again, it's almost a full class. But the AC system is beginning to work a little more. And then by this time, there's hardly anyone in the room, just at most 3 hours. And it seems like it bothers me worse. But actually, this started right at the end of my other class. So I don't know. I don't know why. I'm fine in the morning, and about this time of the day, I can hardly breathe. Maybe it's allergies, or maybe there's something in the ventilation system that it slowly builds up. I don't know. Well, what we're wanting to do is first multiply these two. Can we? Yeah, this is a 3 by 3 times a 3 by 2 is going to give you what? What size? Second? 3 by 2. So it'll be that size. Okay, that first entry, what would it be? 6. Okay, 6 plus 2. Yeah. Remember, this is the 1 entry, first row of that by first column of that. So it'll be 6, 8 is 2. Got it. Next. One. Okay. Next. Yeah. 2 by 1. 2 1 entry here. Second row, first column. Right? Second. Plus 6. Right. Good. Next. That's it. Okay. Next. -1. Next. Right? All right. All right, that's AB. What then is AB transposed? Okay. Exchange the rows and columns. So what I do is take that first column and write it as a row. 2, 6, minus 1. Second column. Perfect attendance today. Way to go. Okay. All right. All right. And what would be next? Okay. And if you preferred, you could have done the first row as the first column. 2, 1, 6, -1, -1, 2. Either way you want to do it. Just exchange rows and columns. Right? Okay. So we've done that part. Now it says, let's see if that's equal to B transpose A transpose. So we'll need first B transpose. What would that be? Whoa, that is really not pretty. Need to have it a little more elevated, that's it. What would that be? Okay. And how about A transpose? All right. Now let's multiply those in this order. Now first, are the sizes right? What's the size of B transpose? And the A transpose? Can you multiply those? Yeah, that gives you what answer? 2 by 3. And AB transpose was 2 by 3. So far, that's looking all right. So 2 by 3. All right. Let's start with the 1 entry, and that would be first row of B transpose times the column of A transpose. transpose. And what does that give us? Second? 6? No, plus 2. 6 plus 2. It's this row times this column.
Oh, I'm looking at the one.
Right.
I'm looking at AB.
Yeah.
Okay. Okay. So we have 6 plus 2 minus 6 plus
2, right? All right. Next.
2.
Wait. Right, that's a 1 there, isn't it? Are you doing this one?
Yeah.
That's a 1. A transpose, that would be a minus 1.
Oh. So minus -3.
Got it? We're doing the 1, 2. So it's first row, second column.
Okay. Yeah, so -3, 0,
6. Here. Oh, you were ahead of me. I'm sorry. Okay. Next.
0,
-1. Okay. Next. 1, you said? Yeah. Okay. Okay. Yeah, okay. I got lost here for a minute. Yeah. Yeah. First, second row, second column, yeah. Okay. -2 what? -2. Right. Okay. 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 Well, I think I did something wrong. Let me. This entry is 2, 2. So second row, second row, second column. -1, 0, 0. It's just a -1, isn't it? Okay. I couldn't hear what you said, and when I looked at it, I said, that can't be right. That's a -1. Okay. Okay. And then uh-huh. Uh-huh. 2. And guess what? Sure enough, they are identical. All right. So it does appear that AB transpose is B transpose A transpose. Okay. This is B transpose. Did it again. Okay. And these two are equal. Okay. Let's do example 10. We just did example 9 at the top of 58. We're doing example 10 in the bottom half of 58. Okay, here's a matrix A. One, 3, 0, -2, -2, -1. Okay? It says find the product, and the product is going to be A times A transpose. So the first thing you got to do is tell me what A transpose is. And you tell me. -2? Is it? Yeah. Got it. Okay. come on, we were just talking, or I was talking. I came up with another proposal of why my head clogs up. Okay. I don't know if this is right or not, but it sort of fits. They usually don't turn on the ventilation system until right at 8 o'clock in the morning. And my first class at 8 o'clock in the morning is a huge class. It's usually right around 30 students in here. Almost every desk taken. So I just have a feeling that it's one of two things. Either it doesn't start cooling very much because you got all the people in here. And then my second class is right around 15 to 17 students. So it doesn't drop off much either. But at the end of that class this morning, suddenly my head is clogging up again. It wasn't just this class. And then we come in here and it's just 3 hours. And now the system's running full blast. So either it's cooling better or more, and I'm getting that like we talked about last time, or it starts pumping out pollutants, and all morning long I just get feeling more and more of them. I don't know which it is, but at the end of the last class I had to go down and just clear my head because I started the day fine. But
you should be better inside the building once the cold air starts coming.
What's that again?
I said you should be better once
once
the fall and winter comes.
Yeah, unless it's the pollutants, and then I'll be the same. But yeah, I'm waiting to see if that's going to help. You're absolutely right. Okay, so here we have A, and we wrote A transpose. Now we're going to do the product of A times A transpose. And can we even do that? You can? What would be its size?
Yeah, it'll be 3 by 2.
Oh, what?
3 by 2.
Don't think so. What is this one?
That's a 3 by 2.
3 by 2 multiplied by 2 by 3. It's going to be a 3 by 3. Okay? Okay, let's start with one of them. And what do we have? I don't think so. This is the 1-1 entry, right? The first row by first column. 10, right? Okay, so that's going to be a 10. It's a 10. Okay, never mind. Okay. Next.
That'll be a -6.
-6. I'll buy that. -5. Very good. Next.
And that would be a -6.
A what? Yeah, -6. Okay, yeah, I understood you. -6. Got it.
Then that would be a +4.
Got it.
And then that would be a +3. No, +2.
2. Okay, got it.
Oh, -5.
-5.
+2.
Got it.
5.
Okay. Agreed? Okay. Now, they said something else. Find the product and show that it is symmetric. What do we mean by symmetric? He's having the same problems. Sounds like he's congested also. Okay, what do we mean by symmetric? basically means ignore the main diagonal. Ignore it. But look at what's across it. Minus 6, minus 6, minus 5, minus 5, 2. That's symmetric. Doesn't matter what these numbers are, but across it, treat that like a mirror, and if everything on either side of the mirror, except for the mirror itself, are the same, then you've got a symmetric matrix. And sure enough, that's a symmetric matrix. Now, it also, it says, that the A transposed is symmetric. And what that means, okay, so of course if you then transpose this matrix, its first column is going to be that row, so that's the same as this row. And its second column is going to be this row, which is the same as that column, right? And its third column will be the same as this row, which is the same as that column. So in other words, A transpose, if it's symmetric, then that's the same as A transpose, because they're the same. Now what they didn't do here, and it's not going to be hard to do, is let's do it the other way. Let's do A transpose A. Can you multiply that? What I'm going to do is, just to make it a little easier, write A down again over here, and that's going to be 1, 3, 0, negative 2, negative 2, 1. Can you multiply those two together? A transpose times A. What you think?
Yeah.
Why?
Because 3 by 3 and 3 by 2 matrix.
Okay, this is a 2 by 3. This one's a...
I think it's talking about A transpose. No, I think it's talking about A and what we just worked out. That A transpose.
Okay, yeah, we already showed that's the same as A transpose. Now, I didn't write it out, but if you did, if you wrote that out, interchange rows and columns, the first row here is going to be this column, which is the same as the first row. And then the second row here will be that column, which is the same as that row. And the third row here would be the same as this column, which is the same as that row, okay? So yeah, we know this. But what I'm saying, the book didn't say, let's investigate A transpose times A. Can we multiply those two together? A transpose times A. I wrote A again there.
Yeah, we can.
And what size will it be?
2 by 2.
Say again?
2 by 2.
2 by 2, you're right. Okay? Because this is a 2 by 3, this is a 3 by 2. You can multiply them because these are the same, and you wind up with a 2 by 2. So let's multiply and see what we get.
You will get that would be 10.
I don't think so. Okay? This is the 1, 1 entry. It's the first row here by first column here.
Okay. 1, 0, 4, 5.
5. Okay. So it'll be a 5. Next.
That would be 3, 2, 3, that would be a 6.
A what? 3 minus 2. 1. Exactly. Okay? You see? Okay. It's the 1, 2 entry. So First row, second column.
Okay.
3, 0, minus 2.
I may have taken it to 3, 1.
Huh?
3, 1. I may have taken it to 3, 1. 3, 1 supposed to be 6.
Okay. Okay. Next.
I'm in a 5. 3. Yeah. 3, 1 entries. 2, 1 entries. 5.
Okay, that's what I had too, and that doesn't make sense. That's a 3, 0. This isn't working, is it? Huh. Oh, I botched something. That's a -1 down there. When I wrote it again, I left off the minus or it didn't write 1. So let's start back. I don't think it's going to mess up the first one. That first 5 is fine. Okay. Whew. Okay. Let's do the 1, 2 again. Five. Okay. And okay. All right. Okay. I'm sorry. Yeah, it will be 3 plus 2 is 5. Got it. I was doing the last one. Okay. Second? 14, is that what you said?
Yes, sir.
Yeah, that's what I got too. And is that a symmetric matrix? Now this is a pretty simple one. Ignore the diagonal, and sure enough, 5 and 5 are the same. So yeah, very simple, but symmetric matrix. So it goes both ways.
So that's the section about making it symmetric.
That's the thing. If you multiply a matrix by its transpose, you're always going to get a symmetric matrix. We did that the first time in the 3 by 3. Again, ignore the main diagonal, then use it as a mirror and everything's the same. So, yeah. And by the way, when you multiply any matrix by its transpose, the product is going to be a square matrix. That was a square 3 by 3, that was a square 2 by 2. So you can talk about symmetric matrices if they're square. If they're not square, they can't be symmetric. Okay. All right, homework exercises. Do any of the odds 1 through 5, any of the odds 7 through 11, any of the odds 15 to 19, do 21, do 23, do 25, do 27. Then do any of the odds 29 through 33, do 35, do 37, either 39 or 41 or both, and either 43 or 45 or both. Now, it said 45, you might need a graphing calculator, but I'll let you decide that. That was 43 or 45. Beginning at 47, that's a true-false statement. Don't expect to see too many of those on the test. You usually won't, but it's still a good thing to think through. And then 49, I think it's a pretty straightforward problem. I'm sorry. Now, 51 looks like it's kind of tricky. But once you do very much with it, I think you'll find it's not nearly as bad as you thought. 53 is a sort of a fun problem. All right, 55. I think you can do that one. And then from there on, though, 57 through let's see, 55, I guess. 65. 55 to 65. I can't talk. I think well, those are mostly proofs and things, so if you want to, you can. If you don't want to, you can give it up. Now, both of you are pre-engineering, right? Or am I wrong? Mechanical, and you're mechanical. Oh, both mechanical. Okay, one of my other classes, both of the guys are civil. So y'all are hanging together, aren't you? Okay. Now, remember I've told you before, some of this book does it way more than I think they should. They introduce new concepts in the exercises, which to me is not the place to introduce them. You introduce that in the chapter and then give problems for the exercises. But we've already mentioned what symmetric matrices are, but now they come up with skew symmetric matrices. And they tell you what it is. 67, 69, you can do either one of those if you want, or both. And then there's some more proofs, 71, any of the odds, 71 through 75. 75 may be a little bit less of a proof, but it just, if you don't want to do those, you don't have to. Okay. Oh, man. So let's go on to, goodness gracious. Lighting up again. Why does this happen? I can hardly breathe. Would you object too much if I run down and get something to drink? I just feel like my whole head is dry. So let me just pause this. I'm so... All right. Wow, sorry. So 2.3 is talking about the inverse of a matrix. Okay? It's funny, this morning's pre-calculus algebra class, I introduced the concept of inverse of a function. We talked about inverse operations you've done from the beginning. Addition undoes subtraction, subtraction undoes addition, multiplication undoes division, division undoes multiplication. Powers undo roots, roots undo powers, you know, logs undo exponents, exponents undo logs, you know, we've had those operations. And then in pre-calculus algebra, you did functions. I just mentioned two functions, exponentials and logs. And remember, an inverse of a number is usually its multiplicative inverse. It could be its additive inverse, but one of the other. When you do an inverse of a variable, it's almost always its multiplicative inverse. X, 1 over x, that kind of stuff. Okay? But when you do an inverse function, they're functions that undo the whole function. So they're no longer reciprocals at all. Well, now we have another kind of inverse, inverse of a matrix, and it's not the same as either one of those. Okay? And yet it uses the same notation, that -1 superscript. Now it says in section 2.2, the one we just did, we discussed some of the similarities between the algebra of real numbers and the algebra of matrices. This section further develops the algebra of matrices to include solutions of matrix equations involving matrix multiplication. So to begin, let's consider the real number equation, really simple thing, AX equal B. Okay? Real simple equation. If you want to know what X is, you divide by A, right? Well, A, dividing by A is the same as multiplying by 1 over A, right? Well, 1 over A is A to the minus 1. Okay? So you can multiply both sides of the equation by A to the minus 1. Now, I was starting to do this and say A to the minus 1 here. But to make it look more like a matrix, you always multiply by the same size. If it was a number, it doesn't matter. If that was 3x is equal to 6, you can multiply the first side by 1/3, second side by 1/3. If you did 1/3 by 6 or 6 by 1/3, you get the same answer. However, with matrices, you got to be careful and do it from the same size, because matrices, matrix multiplication is not commutative. Okay? So your answer then, this goes to 1, x is equal to A inverse times B. Okay? Where with a number, that means 1 over, multiplicative inverse. Okay? Now, actually in the trig class today, we did the inverse of a function when you had a big, long, hairy sine of something another is equal to something else. How you find out what the something another is do an inverse sine of both functions, of both sides. And that's the same type thing we're doing here. This is with numbers. You also do it if you had sine theta is equal to B. How you find out what theta is, if you know what B is, you do theta is equal to inverse sine of B. Okay? So you do the same process. We use even the same notation. But this is an inverse function. That's the multiplicative inverse number. Okay? Well, if that's not enough, we're going to be doing the same thing with matrices. At least the notation looks the same, but in reality, it's a slightly different process. So let's start with the concept of a matrix A. Now this time A has to be a square matrix, n by n. It cannot be rectangular, it has to be square. Now we say that matrix A is invertible. In other words, it has an inverse. Okay? Now there's another word for invertible. Non-singular. Now, I don't have any context to give you to get why that's true yet. You'll get used to seeing it, so get used to it, okay? Invertible or non-singular. It is invertible or non-singular when there exists another n by n matrix, okay, let's call it B, such that, and here is the test to see if these are invertible, inverses of each other. If you take AB, and when you multiply it together, you get the same as you do when you get BA. That's usually not the case, is it? Usually, multiplication of matrices are not commutative. Usually, you cannot do that. But if you can do it, and the product of those two matrices is the identity matrix of the same dimension, because remember, A was n by n, B was n by n, so the product's going to be n by n. And if that product, for either way you did it, turns out to be the identity matrix, then you have an invertible matrix, or non-singular. okay? Where I sub n is the identity matrix of order n. The matrix B is called the multiplicative inverse of A, or just the inverse of A. A matrix does not have an inverse is called non-invertible or singular. So if that isn't the case, then it's a non-invertible or a singular matrix. So invertible means it does have an inverse, that makes it non-singular. If it doesn't have an inverse, that makes it singular. Okay, so if it's non-invertible, it's singular. Okay, so one subscript of this, follow-up to this, if it's not a square matrix, you cannot have an inverse, okay? If it's a matrix is not square, there is no inverse, okay? And the reason for it, let's say that you had a matrix A which was M by N, and a matrix B which was N by M. Well, if you did AB, you get an M by M matrix, but if you did B by A, where B was N by M and A was M by N, then that answer would be an N by N square matrix. Can't do that. I mean, wait, you can do it, but the thing is, this cannot equal that because it wouldn't be the same dimension. Okay? They could not be equal to each other because they're not even the same size. So, to begin with, A and B have to be the same size. I mean, square matrices, same size square matrix. And then the product has to be the identity matrix of that size. Identity matrices are always square too. Okay? Now the next theorem, I think, builds on that even. So let me get space enough to write it. If A is an invertible matrix, then its inverse is unique. If A is invertible, that implies its inverse is unique. It has one and only one inverse. Okay? And the inverse of that matrix is then called A inverse. And we use that same notation we did for multiplicative inverse, for inverse functions. We use the same notation for inverse matrices, understanding, however, that they're not always equivalent. Okay? Now, let me give you just a little bit. Let's say we had a number. Okay? A, little a. Multiply it by its inverse, a to the minus 1. That is the same as a times 1 over a, right? That's a multiplicative inverse. What's that product? 1. Okay? Now, when we have functions, we don't talk about multiplying inverse functions. We talk about composing inverse functions. Okay? If you have f composed with f inverse of x, you're going to get, okay, not the number 1, but the identity function x. If f and f inverse are inverses of each other, and we also do it the other way, the f inverse of f of x is equal to x. Okay? So, what we just said about matrices, if you have A times A inverse, that's going to give you, be the same as A inverse times A. And since you will always, well, either way you multiply those, you're going to get that IN. Okay. So, actually in this case, it's more like the numbers. Think of the identity matrix as being more like the number 1. But guess what? We call this an identity function too. So the identity matrix, identity function, they have the same names, but these have closer to the same values. This is 1's on the diagonal, 0 everywhere else. So not quite equivalent, but awfully close to it. Okay? All right. Now, the little proof here for this theorem, if A is invertible, then its inverse is a unique value. Okay? This is fairly easy to prove. You're given this, that A is invertible. That means there exists an A inverse. Okay? And that product of A inverse is equal to I sub n. Okay? That's what it means if A is invertible. Now, it says that inverse is unique. That's saying, what if there was some other matrix, I'm going to use the same one they do, C, which is not equal to A inverse. Okay? So let's assume that C is not equal to A inverse. But that this is also true, AC is equal to I, and they leave off the N, so I'll leave it off now, and that's also equal to CA. Okay? Now, if we can show that that C is the same as A inverse, then we've got it knocked. Okay? So what we're going to do is up here, multiply both sides by C. So let's multiply C times A inverse. Now if we multiply that way, we do C times I sub n, just I sub n. Okay? They're leaving off the n, so I will too. Okay. Now, by our other definition, associative property, CA, this is equal to CA times A inverse. Okay? And this also would equal, and by the way, C times I is just C. Anytime you multiply by identity matrix, you get the same thing that you started with. Okay? Now, we've already said that CA is equal to I. So this is I times A inverse is equal to C. Well, I times A inverse, multiply I by anything, you get the same thing. This shows that A inverse is C, that's not different from C. Our assumption was it's different from C. This says, nope, it comes back to being the same. Okay? I just thought we'd do that one little proof because it's a fairly easy one to do. All right. Let's just go on and do some exercises. Examples. They're, I think, more fun than proofs. Okay, but that's my bias. Let's show that B is the inverse of A with these two functions. Okay, here's A. Negative 1, 2. Negative 1, 1. Okay. B is 1, negative 2. 1, negative 1. Okay. And my eyes are dry. So we want to show those are inverses of each other. How do we show that? What's true about two matrices if they're inverses? What is true about of the same size? Is that what you said? Yeah, they've got to be. Yeah, you're absolutely right. If they're inverses, they've got to be the same size. But lots of matrices are 2 by 2. What makes these inverses of each other? What would be the condition? What has to be true?
I see what you did, but I'm not sure if this is correct. Is this the correct answer? Based off of matrix A, you put the same numbers in matrix B, but you made the positive numbers in A negative in B.
Okay, that is a pretty good observation. You just switch signs of both numbers. I don't think that in itself would make it an inverse, okay? It is an observation that they are that way. Goodness, my eyes hurt. They're just as dry as they can be. I don't, it hurts to look. Okay, maybe I've been staring at the glare too long. I don't know. No, how you can tell if they're inverses? Multiply them together, and what did you better get? The identity matrix. So let's multiply them together. Let's multiply AB. And what would that be? First, what size will it be? 2 by 2, because both of those are 2 by 2. Okay? First entry will be I'm sorry?
No, it'll be a 1,
positive 1. You got it. All right. The 1 entry would be
second one is
0. Okay. Plus 2 minus 2. Got it. Next one's going to be a 0. Second, 1. Yeah, okay, it shouldn't be a negative 1. Okay, let's see. It would be a 2 minus 1, 1. Sure enough, that's the identity matrix. Is that enough? Well, not really. We also want to see what BA is. Most of the time, matrices multiplication is not commutative. But if they're symmetric, if they're inverse matrices, it should be. So let's rewrite A here as minus 1, 2, minus 1, 2. No, minus 1, 1. Mess up that last one every time somehow. Well, okay, let's try it one more time. No. Okay, let's multiply those two together. And what do we get?
positive 1.
Yep.
0.
0. Good. 0 again. Good so far. 1. Got it. Yep. They have to be inverses of each other. So, you think there are any other inverses out there of A? No. If you find it, that's the only one there is. It's unique. Okay. All right. Oh, no. It's time. How did that happen? I guess that little break I took in the middle lost me some time. Okay, we'll start with example 2 next time. Okay, and hopefully I won't have this next week. I don't know what the deal is. Okay, let's do a few homework exercises. In this, I think you can do any of the odds 1 through 5. Okay? That's all you need to do in this section. And I haven't said it every time, but let me say it again. Remember, this author, same as the author we used for Math 112 and 113, he has this thing called calccheck.com that has all the odd number exercises worked out. So that's why I assigned the odd numbers. If you can't get the answer they have in the back and the odd numbered answers are in the back, you can go to calctech.com, free website, and check. Now, I did find out one person said yesterday that when they went to it, they found that it was restricted to just certain hours. I didn't know that before. I don't know if that's true or not. So check it out and see. It may be that you actually have to have a person on the other end to interact with. I don't know. Calctech.com sounds like maybe you do. So, I don't know the answer to that, but give it a shot. All right, any questions? Then have a good weekend. Of course, working on linear algebra will make it good, won't it? Okay. Oh, man, I'm so sorry.